Hello! By watching this video, you will learn what Hadoop is, why it was created, and what it is used for. I'm sure you recognize most, if not all, of these companies. What they have in common is that they all receive significant benefits from using Hadoop. You probably remember this news story. When Orbitz used Hadoop to correlate hotel bookings with their customers' web browser software, they discovered that Mac users tended to reserve rooms that were about 30% more expensive than rooms that Windows users booked. With this newfound insight, Orbitz decided to present Mac users with a list of hotels in a different sort order, a move that caused their average price paid per room to rise. Hadoop is also used to improve hotel rankings and to measure and track how long it takes users to download web pages. You probably also remember when IBM's Watson computer competed against two Jeopardy champions for $1 million prize. Hadoop indexed 200 million pages of unstructured content, including the entire contents of Wikipedia, so that Watson could respond to natural language queries in less than 3 seconds. In this eBay session, I entered the word "I paid," but eBay's search engine was smart enough to know that I was probably looking for an iPad. Hadoop has proven helpful in deciphering patterns of misspelled words. So now eBay's search engine knows to look instead for an actual word when users type certain queries incorrectly. You may recognize this LinkedIn page, which presents you with a list of people you may know. Hadoop scores 150 billion relationships per day using a statistical model to determine the probability that you may know another member. I typed the word playpen into Google, and the first match that was displayed was from Walmart. Walmart bids on Google and Bing keywords to drive internet traffic to Walmart.com for specific products. Hadoop enables Walmart to collect information about millions of keywords and come up with optimal bids for each word. eHarmony uses Hadoop to rescore relationship matches whenever people sign up or when existing members update their profiles. Hadoop analyzes the effectiveness of TV ads so that eHarmony knows how much each commercial yields in new customers. At the turn of the century, the volume of data being collected by Google grew dramatically. Look at the huge jump between 1998 and 2000. It was between these years when Google really started having trouble indexing the entire internet. So what was causing the problem that Google faced? The traditional way of storing and analyzing data on top of a single relational database with single process execution could not scale up at the same rate that data was growing, so something needed to be done. An option to solve the problem was to use distributed processing to scale out, despite the inherent complexity involved in running such systems. Initially, the time spent by developers on the mechanical aspects of distributed processing was much greater than the time that they spent on analytical programming. Something further needed to be done to make the mechanical aspects automatic so that developers could be more productive. So the good news and bad news is we now have big data, but how are we going to store and process it? Although the storage capacities of hard drives have increased massively over the years, their access speeds have not kept up. Back in 1990, the storage space and transfer speed of our drives were very low compared to modern drives. 20 years later, storage space increased by 77,000%, but transfer speed increased by only 2,000%. One way to reduce the time needed to read all of the data is to read it from multiple disks at the same time. If we had 100 drives like these, each holding 1/100th of the data, then working in parallel, we could read 1 terabyte in less than 2 minutes. So where did Hadoop come from? Google was looking for a way to index the entire World Wide Web every day, and they accomplished this after creating the Google file system and the MapReduce programming model. A software engineer named Doug Cutting, who had previously worked at Excite, Apple, and Xerox, got the inspiration for Hadoop after reading papers about the Google file system and MapReduce, which described a design paradigm that used commodity hardware to effectively process massive amounts of data in a fraction of the time previously required. As the ecosystem around Hadoop evolved, the complexity of dealing with distributed processing and distributed files has become more hidden from developers, and Hadoop's adoption rate has increased. But there's more to the solution than simply being able to access data in parallel. The first problem to solve is hardware failure. As soon as you start using many pieces of hardware, the chance that one will fail is fairly high. A common way of avoiding data loss is through replication. Redundant copies of data are kept by the system so that in the event of a failure, there is another copy available. The Hadoop distributed file system offers a solution to hardware failure. It is a file system that splits, scatters, replicates, and manages data across the nodes of a cluster. HDFS enables self-healing, high-bandwidth cluster storage. The second problem that needed to be overcome is that most analysis tasks need to be able to combine distributed data in some way. For example, data read from one disk may need to be combined with data from any of the other 99 disks in the cluster. But combining data from multiple distributed drives is challenging. MapReduce offers a solution to this problem. MapReduce is a computational mechanism that executes an application in parallel by dividing it into tasks, co-locating the tasks with data blocks, redistributing intermediate results, and managing failure across all nodes. MapReduce enables distributed, fault-tolerant resource management and scheduling, coupled with a scalable data programming abstraction. So this is what Hadoop provides: a reliable shared storage and analysis system. Storage is provided by HDFS, and analysis is provided by MapReduce. So how can we sum up what Hadoop is? Here's a shot at a couple of definitions. Hadoop is a fault-tolerant programming framework that supports data distribution and process parallelization using a scale-out architecture that's built with cost-effective commodity hardware. Hadoop is an open-source data processing technology credited for catalyzing the big data movement because it takes advantage of large clusters of industry-standard servers to create a single, highly available environment capable of storing and managing petabytes of data. It would also be good at this time to dispel a few myths. Hadoop is none of these. It's not a database like Oracle, it doesn't have a graphical user interface like QlikView, and it's certainly not a GUI data integration platform like PowerCenter. It isn't any of these. This is Hadoop. Well, this is really Hadoop. Hadoop is the name of this toy elephant. This is Doug Cutting, whom I mentioned 5 slides ago. He started the open source Hadoop project. When it came time to name the project, he chose the name his son had given to his toy elephant. The word Hadoop was short, easy to spell and pronounce, meaningless, and not used anywhere else. So there's another mythbuster. Hadoop is not an acronym. It's not pronounced Hadoop, nor is it pronounced Haydoop. It is pronounced Hadoop. Famous computer scientist Grace Hopper was credited with the following quote, which she spoke 30 years ago, but it's still relevant today to the kind of hardware system that Hadoop employs. In pioneer days, they used oxen for heavy pulling, and when one ox couldn't budge a log, they didn't try to grow a larger ox. We shouldn't be trying for bigger computers, but for more systems of computers. The architecture that Hadoop employs is like the opposite of virtual machine architecture. VMware is all about taking one physical server and chopping it up into many small virtual servers. On the other hand, Hadoop's architecture is all about taking many physical servers and merging them together to look like one big massive virtual server. Hadoop jobs are data intensive and process entire data sets, whereas VMware is good for compute intensive jobs that use many cycles on data subsets. Now we'll learn a little bit about cluster architecture. A node contains a set of commodity cores and memory that are attached to a set of disks. A stack of nodes form a rack, and a group of racks form a cluster. Hadoop was designed to enable applications to make the most out of cluster architecture by addressing 2 key points: the layout of a dataset across the cluster, ensuring evenly distributed data. A dataset is automatically chopped up and scattered across the nodes of a cluster. And the design of applications to benefit from data locality. This is such an important concept. Data is processed by cores that are co-located in the same node with the disks that holds the data, eliminating data transfer across a network. The Hadoop distributed file system automatically divides a dataset into equal-sized file blocks, which are sized to be a multiple of the storage block size. A file block is the unit HDFS uses to distribute the chunks of a dataset across all of the disks in the cluster's nodes. Since cores, disk, nodes, and racks can fail, the same file block is stored on multiple nodes across the cluster. The default is 3 copies of each block. So, if a block cannot be processed on a certain node, then one of its copies is automatically processed instead. MapReduce sees a computational task as consisting of 2 phases. During the map phase, all nodes will do the same computation, but against the part of the dataset that is co-located in their node. Here, I'm illustrating each map performing a word count operation on unstructured data. Each time the map function comes across a word, it counts it by creating a key-value pair that contains the word and a count of 1. The reduce phase is used to sum the results obtained by each node to reduce the output of the map functions to a single list of key-value pairs. A node is selected to execute the reduce function, and all other nodes send their key-value pair list to the designated reduce node. So you see here, the reduce function's output is a summary of the number of times each word was counted by all of the maps. Now we'll look at a timeline that shows some highlights from the birth and use of Hadoop over the past decade. In 2003, Doug Cutting was working on an open source app named Nutch, which attempted to crawl the web to build a search index. He was able to get Nutch to run successfully on a 4-node cluster, but that was hardly at web scale. Later in 2003, at an operating system conference, Google published a paper about the Google file system, a highly scalable file system. In 2004, Cutting created the Nutch distributed file system, an open source clone of the Google file system. Later in 2004, at another operating system conference, Google published a paper about its MapReduce programming model. In 2005, an open source clone of MapReduce was created by Cutting for Nutch. Eventually, Cutting was able to make Nutch MapReduce run successfully on a 20-node cluster. In 2006, an Apache project was launched to combine MapReduce and the distributed file system into a new ecosystem named Hadoop. Later that year, Yahoo was able to run Hadoop on a 600-node cluster. By 2007, Yahoo was running two 1,000-node Hadoop clusters. In 2008, Yahoo used a Hadoop cluster to sort 1 terabyte of data in only 209 seconds. In 2009, Yahoo lowered the 1 terabyte sort record to 62 seconds using Hadoop. By 2010, Facebook was using a 2,000-node Hadoop cluster with 21 petabytes of data. By 2011, Yahoo had more than 42,000 nodes in several Hadoop clusters that contained hundreds of petabytes of data. By 2012, Facebook was loading a half a petabyte of data into their Hadoop clusters every day. In 2013, Hadoop vendor MapR used Hadoop to sort 1.5 terabytes of data in less than 1 minute. Hadoop is truly the quintessential Silicon Valley story. If you want a great shot at starting a successful tech company, you should attend Stanford University. Sergey Brin and Larry Page attended Stanford, as did Doug Cutting and a guy named Omer Awadallah. Sergey and Larry started a web search company named Google in 1998 while they were PhD students. In 2003 and 2004, Google published papers about Google MapReduce and the Google file system, and Doug Cutting used these papers to create open source versions. After receiving his PhD, Omer went to work for Yahoo and led their BI team. Doug went to work for Yahoo, so instead of trying to enhance Hadoop by himself, he led a whole team of Hadoop developers. At this same time, Jeff Hammerbacher, who was the Harvard math whiz who coined the term data science, led a team of data scientists at Facebook, and Christoph Basilia founded Google's academic cloud computing initiative. These four gentlemen left their respective companies and founded Cloudera, today's leading distributor of Hadoop. Yahoo ended up spinning off its large Hadoop development team into a new company named Hortonworks, which was named after the elephant in Horton Hears a Who. So, the core of Hadoop, which is MapReduce and HDFS, they came from Google, and the two most used Hadoop programming languages, Hive and Pig, were created at Facebook and Yahoo. In addition to the Apache Software Foundation, you can also get distributions of Hadoop software from over a dozen vendors. Here's a look at the major Hadoop vendors and when each started distributing Hadoop. In a typical data warehouse environment, we mainly use data integration techniques to load structured data from internal and external sources into an enterprise data warehouse. In the future, Hadoop usage would not necessarily replace anything we do today. We could load dark data from internal and external sources into Hadoop. Dark data is data that we don't use today, but may contain useful actionable insights. This raw data is copied directly into Hadoop. Analytics can then be performed immediately on the raw data. We may want to load some of the results of MapReduce analyses into the EDW to enable further processing, like correlation analyses. We may want to load some existing data from the EDW, like call logs or web clickstream, into Hadoop to take advantage of its text analysis capabilities. When we look at a consumption timeline, the number of days required to go from the initial acquisition of the raw data to analyzing the data is much less when using Hadoop, which is another major benefit. Time to market is quicker because the data is dirty. It hasn't been cleansed, standardized, and transformed. Now we'll look at the differences between a relational database and Hadoop. A major difference is in the timing for when you need to create a schema for your data set. With an RDBMS, you need to define a schema before you write data to a table. And with Hadoop, you just do it before you read data from HDFS. When loading data into a database, you use an ETL process, but loading data into HDFS simply requires a file copy operation. This enables unstructured data to be loaded into Hadoop. With Hadoop, you don't have to describe the shape of the data until you want to process it. As you can imagine, with Hadoop, there is less need for data modelers and DBAs. In terms of data access, it is much faster to read from a database, but there are far less procedural steps involved to write data into Hadoop. A major advantage of a proper database is that the data that users will consume has been pre-processed by ETL jobs to ensure a cleansed and standardized asset. And while Hadoop data is raw and dirty, it does allow consumers to access unstructured data for text analysis. With Hadoop, you will hear a lot of talk about data lakes and data ponds. Streams of data from many sources flow into the data lake that HDFS provides. Consumers can then wade through the lake and perform data mashups. After the data has been refined inside Hadoop, its resulting information can be fed into an EDW. This is especially true when dealing with text. Unstructured data is not valuable until it is parsed into structured assets that can be analyzed. Smaller data ponds can also be created in HDFS to segregate sensitive data from the common lake. One of the use cases for Hadoop is as an active archive. Instead of archiving historic warehouse data onto tape devices, you can move it onto HDFS disks where it can be accessed in the future if the need arises. There are several important differences between data warehouses and data lakes. Sometimes data is copied into a lake without an immediate need for analysis. The raw data will be available when a need does arise. When people drink from a lake, they know what they are consuming is raw and dirty, and it is up to the consumer to refine the lake data before it can be of value. Data in the lake is considered to be first and foremost assets for batch processing. Real-time analytic and BI applications consume data from a warehouse. A big advantage of using an EDW is that consumers can consult published metadata before they begin processing its data. An important thing to remember is that the data lake does not support update transactions. Data is written to the lake once, and then it is available as is to many consumers. One of the best uses for a data lake is to store and process unstructured data. But text is only useful and valuable to us after we give structure to it. Because of its schema on read architecture, it is easy to copy unstructured data into Hadoop. A programmer can then use the data as a source into text analytics programs, which extract valuable information and store it in a schema, allowing for further exploration inside Hadoop. The refined structured data can also be copied into a relational database where it can be analyzed using familiar BI tools and SQL. The refined data can also be copied into an analytic environment like SAS and used in various models. Now we'll compare the difference between moving data into a data warehouse versus moving it into Hadoop. When raw data is exposed to an enterprise, it goes through many processes before it can be consumed. It takes a whole team of people to discover, transform, deploy, and load raw data into a proper EDW. But the final product is usually worth the wait because what EDW consumers will access is high quality, high value data that has been cleansed and standardized. On the other hand, moving data into a data lake takes one simple step, as the data flows into the lake as is. So while access to data in the lake is granted very quickly as compared with the EDW process, the type of skills needed to analyze data in Hadoop are quite advanced, as the consumer needs to wear many hats, those of a SME, a programmer, and a data analyst, because what they will find in the lake will be of uncertain quality and may be full of noise. It will be up to them to derive value. When people talk about Hadoop, they are often referring to more than just its core elements, MapReduce and HDFS. There is a whole ecosystem of open source projects that work with MapReduce and HDFS. Apps with silly sounding names like Uzi, Chukwa, Pig, and Scoop. In this slide, I took the software components from IBM's Hadoop distribution and divided them into logical groups to show the ecosystem at a high level. The data access layer contains software to copy data from databases and logs into Hadoop. The data storage layer contains software to store and manage data. The data processing layer contains software to analyze unstructured, semi-structured, and structured data. The analytics methods layer contains libraries of analytic and indexing functions. The process management layer helps the other Hadoop software work together. So, what kind of people use Hadoop? Data scientist is the term used to describe people with extensive skills in three areas. You can't be just a programmer to use Hadoop, but programming skills are a definite requirement because Hadoop is a programming environment. You also need to be able to think like a statistician, build models, and use data mining techniques. And since assets in the data lake have not been neatly packaged together by business analysts and data quality experts, you need to fully understand the data's business domain.